Recording in progress.
Hi students, in this lecture we are going to learn electric field lines and electric flux. Let us see first what is the meaning of electric field lines. Consider a positive charge. It is a point charge. Consider a positive point charge. Okay. Now imagine a unit positive charge somewhere here. It is a unit positive charge. You can see this positive charge repels this positive charge. Means a force will be along the line showing them and away from them. Means away from plus q. Okay. Suppose I am taking a positive charge here. Again repulsion. That will be away from positive charge. Suppose take now positive charge here. Again repulsion along the line showing them like this. Means away from this positive point charge. That means, so we are taking here lines which are away from positive charge. So this is a point charge which is a positive charge. Whenever we are taking a unit positive charge, this is now repelling. Now we are imagining lines along the direction of field. I am repeating, we are imagining lines along the direction of force because since charge is plus 1, force and field both are same. I am writing here F bar equal to Q into E bar. When Q value plus 1, F bar and E bar both are same. So we are imagining lines along the direction of electric field. So these were calling as electric field lines. We are calling as electric field lines. That means if we are taking a positive point charge, electric field lines are radially outwards. They are radially outwards because when we imagine unit positive charge, it will repel. Therefore, direction of field is away from plus q. That's why because of positive point charge, field lines are radially outwards. If we consider negative point charge, then see what happens if we consider unit positive charge. Now this negative charge attracts this positive charge. That means direction of field is towards minus q. If I'm taking a plus charge here, plus 1, it is now towards minus q. That means field lines due to negative point charge are radially inwards, right? So here we have to remember one important point, that is field is real, but field lines are imaginary. So these field lines are helping us to visualize the electric field. I am repeating, these field lines are helping us to visualize the electric field. Okay. Now see carefully. Here one important point is, so when you are taking a positive charge, field lines radially outwards, radially outwards. If you observe carefully, force by this charge is more if positive charge is closer to the charge, right? If distance is less, strength of the field is more. Distance is more, strength of the field is less. So here what I am saying is, closer to the charge, separation between the lines, you can see spacing, okay? So spacing will be less. As we are drawing lines away from charge Q like this, you can see separation between the lines is increasing. See carefully. When we draw lines away from Q, separation between the lines is increasing, right? The separation more means strength of field is less. I am repeating. You can see closer to charge between the line separation is less. As we are moving away from charge between the lines, separation is more. Separation more means strength of the field is less. That means if field lines are crowded, if field lines are crowded, then strength of the field is relatively more in that region. That is what we can conclude from this one. So closer to this charge between the field line separation is less. Suppose we focus now this way. I'll take different color to make it more clear. Suppose I'm focusing now, let us say this chart, this line and this line. Okay. So when their closure, separation between them is less. As they are moving, as we are moving away from charge, separation between the lines is increasing. So separation increasing means field strength is decreasing. Okay. That means whenever we are having field lines by seeing, we can decide in which region strength of field is more, in which region strength of field is less. So how we decide means if separation between the lines is less, strength is relatively more. If spacing between lines is more, then strength is relatively less. For example, let us take uniform field. So uniform field means modulus of E bar is the same. Direction also same at each and every point. Okay. Then field lines are parallel and equispaced. Field lines are parallel and equispaced. So if you take two successful lines, separation same and they are parallel. So this is now representing uniform electric field. Suppose I'm drawing like this. E bar, one line, next line, next line. If you observe case one and second one, compared to second one, you can see in second one, spacing between field lines is less, right? And here between the lines, between any two successive lines, separation is more compared to the separation in second case, right? That means if this is E1 and if this is E2, okay, then what we can say is by seeing these field lines, strength of E2 is greater than E1. Okay, that means by seeing field lines pattern, we can say in which region field strength is more or field strength is less. Okay, right. So one point is here because of positive charge field lines they are away from, right? Means because of point charge field lines radially outwards, because of negative point charge field lines radially inwards. Okay, and here key point is that, for example, this is now electric field line. It is not a straight line. So how this is drawn means at each and every point, at each and every point, if I draw tangent at this point, that tangent gives direction of field at that point. That tangent gives direction of a field at that point. Okay. For example, take here a positive charge It's a point charge, and this is a negative charge. If you consider in between these two charges a unit positive charge, what is it? Consider a unit positive charge in between the charges. Okay, then positive repels positive, negative attracts positive. Means direction of field is, it is from positive to negative. It is a straight line. So between these two charges, a field line is a straight line. If you consider right of minus q, if you imagine positive charge, direction of field will be towards minus q, means the field line is like this. If you consider left of plus q, it will repel positive charge. Direction is like this. If I'm taking somewhere here, see carefully this point. If I'm taking somewhere here, imagine there unit positive charge. Now this positive charge repels. This positive charge repels. So field will be like this. This positive charge is attracting. So field will be like this. Now at this point, resultant of these two fields will be, it may be like this. So when we draw electric field line, it will be in such a way that this will become tangent to that field line at this point. I am repeating. If we draw field line from positive to negative, then this direction becomes tangent to that line at that point. So it comes approximately, okay, like this, not exactly like this. Okay. So tangent is giving us direction of a field at that point. And if we observe carefully one more thing, field lines start from positive charge. Okay. And field lines end on negative charge. Field lines start from positive charge and end on negative charge. And one more interesting point is, if modulus of charge is more, if modulus of charge is more, then we are having more number of field lines. Okay. If modulus of charge is more, then having more number of field lines. For example, let us take one is, let us say 10 coulomb. Other one is, let us say 5 coulomb. Then when we are making diagram, suppose Q1 is having 100 lines. Then for Q2 only half of that. That means only 50 lines. That means what we can say is number of field lines are proportional to strength of the, or you can say magnitude of the charge. Suppose I'm taking here minus 5, still same number. Okay. Only changes field lines will be towards Q2 if charge is negative. So one important point is here, if magnitude of a charge is more, then number of field lines also more, right? So we got conclusion that field lines start from positive charge and end on negative charge. So from this we can give one more conclusion that these field lines cannot be closed. So electric field lines are open curves, okay? Because starting from positive ending on negative. That's why they are not closed. Okay. Our same point we can explain like this. See carefully. Why field lines, electric field lines cannot be closed. So we can explain using the property of that electric field is a conservative. Since electric field is a conservative, work done by electric field in a closed path should be zero. What is it? Work done by electric field in a closed path should be zero, because electric field is a conservative field. Okay. For example, I am taking this is now field line. What is this? This is now field line. Arrow is like this. Arrow is indicating direction of field. Okay. Suppose we are taking a charge Q along the field line like this. So field line in this way, in the sense, force is now along that line, right? I am writing here this is A, B, C, and D. So while taking from A to B on this positive charge, work done by electric force is positive. A to B. B to C also it is a positive. It is also positive. Next, from C to D, again, electric forces from C to D and displacement also from C to D. Again, by electric force, work is a positive. From D to A, displacement from D to A, electric force also from D to A. That means in this closed path, by electric force, work is positive, 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 and positive. Means total value is now positive. So I'm writing here closed integral f bar dot dl bar is not equal to 0. That means closed integral e bar dot dl bar is not equal to 0. So how we got this one means in the place of f bar, I have taken q into e bar and anyhow charge is not 0, right? That means a closed integral e bar dot dl bar not equal to 0. Okay. That means field lines cannot be closed. They must be open. Means what we're expecting is, we're expecting that one important point here. One important point is that closed integral e bar dot dl bar should be equal to 0. So why it is 0 means because electrostatic field is a conservative field. Okay. So with the help of this property, we can see that electric field lines cannot be closed. Okay. Right. Let us see notes for this one. Right. So to visualize electric field, so this concept given by Michael Faraday. So field lines due to positive charge radially outwards, due to negative charge radially inwards. Tangent drawn to the field lines at a point gives the direction of field at that point. You can see diagrams here. This is a positive charge radially outwards. Okay. And if you focus any two lines, separation between them is increasing as distance is increasing. I am repeating. If you take any two lines, as distance is increasing, separation between those two lines is increasing. Its meaning is strength of the field is decreasing. So less spacing, more strength. More spacing, less strength. Okay. Now see here negative charge radially inwards. Okay. Next. So two positive charges. So how field lines are. Okay. And this is a negative and positive charge. Field lines pattern like this. Right. Next. Field lines start from positive charge and end on negative charge. Okay. They're open curves. If field lines are crowded in a region, strength of the field is relatively more. Widely spaced, strength of field is relatively less. Right? So field lines are open curves. They do not form closed currents due to conservative nature of electrostatic field. Just now we have discussed, right? Next, no two field lines intersect. Why? Because if they intersect at that point, two tangents can be drawn. That means at the same point, electric field is having two directions, which is observed. Okay, I will explain this for this point once again. See carefully. Suppose this is one field line, and this is one more field line. This is one more field line. If they intersect, what happens? One tangent comes along the yellow line, and one tangent comes along the blue line. Means at same point, electric field having two directions. Okay, and that is not possible because at a point, field having only one direction. That's why no two field lines intersect each other. Okay, right. And next important point is that which we have discussed. Electric field is real, but field lines are imaginary. Okay, right. Let us now discuss electric flux. Okay, see what is the meaning of that electric flux. So we have now discussed regarding field lines. Field lines. Suppose I am taking field is uniform. Field uniform means field lines they are parallel and equispaced. So I am drawing here parallel and equispaced. Suppose this is now along x-axis. Okay, along x-axis. Now consider a surface. Okay, consider a surface. For example, for to understand easily, take one rectangle. Take one rectangle here. Take one rectangle which is in xy plane. Which is in xy plane. Now see carefully how many lines are passing through that surface. Okay. So I have taken this rectangle in xy plane and field lines are along its axis. Okay. So here no field lines are passing through the surface. Okay, they are just going like this. Okay, not passing through surface. Okay. That means we say flux through that face is zero. Through that surface is zero. Suppose consider, this is take it as a case one. Let us consider same field lines, same field lines, but I'm imagining same rectangle, it is now YZ plane, YZ plane, okay? So YZ plane means if we see from this side, it appears just like a line, okay? I'm repeating, we have taken out this rectangle in YZ plane. Then how it appears for us? This appears just like a line. Then see, all these lines are passing through that plane. All these lines are passing through that plane, right? Or through that surface. See difference between the first one and second one. In second one, all field lines are passing through that surface because we have taken surface in YZ plane. Surface is in YZ plane. Okay. But in first case, we have taken in XY plane. In XY plane. So no field lines part passing through that surface. Okay. Now we want to generalize this. In case one, no field lines are passing. In case two, all field lines are passing. Okay. I want to generalize now this. That is this calculation, how calculation is done. Flux. This is the notation for flux. That is calculating as integral e bar dot ds bar. Okay. E bar electric field vector ds bar. It is area vector. So we are knowing that area is a vector quantity. This is what we have learned in vectors, right? While calculating area of a parallelogram, we have taken a bar cross b bar, which is a vector. Okay. So for a plane, area vector direction is given by normal to the plane. I am repeating. If you are having a plane surface, area is a vector quantity. It has direction, and the direction is normal to plane. For example, I'm taking here a plane. Let us say like this. I'm taking a plane like this. For this one, normal. Normal means having one possibility of upwards and one is downwards. So we can take any one of these two. We can take any one of these two. Okay. That means direction of area vector is now normal to the plane. Okay. And if you see in first case, between field vector is in this case, it is along x-axis. I can say E into I cap along x-axis. Coming to area vector, it is, we have taken xy plane means it may be plus k cap or minus k cap. See carefully. When we have taken plane, that rectangle in xy plane, it's normal either along positive z-axis or negative z-axis, right? If you take E bar dot A bar, this is I cap and this is a k cap dot, it becomes 0. That means no field lines are passing through that surface. That means there is no electric flux. Okay. Coming to in this case, E bar. E bar is, it is along x-axis and we have taken this plane. It is in YZ plane. YZ plane means area vector will be direction part. It may be minus I cap or it may be plus I cap. Okay. So I cap dot I cap. Okay. That means when we are having the field normal to plane, I am repeated, when field is normal to plane, or we can say when field is along the normal to the plane, when field is along the normal to the plane, in that case, flux will be maximum. Getting the point means if you are taking angle is 0. So if you want to generalize the calculation of electric flux, phi equal to integral E bar dot ds bar. When angle is 90, no flux. If angle is 0, flux is maximum. Okay. That means flux is a measure of number of field lines. More flux means more field lines are passing. Less flux means less field lines are passing. Okay. Right. Now focus here one more important point. Suppose I'm taking here one surface which is closed. It can be any shape. This is one surface which is closed. Okay. Consider a point charge outside. Consider a point charge outside. Suppose Q. Now field lines from this charge. We are knowing radially outwards, right? Radially, radially outwards. Radially outwards in all directions like this. If you observe carefully, any field line that is a passing to the surface means that is entering into surface, it is also leaving surface. Okay. If I take one more line, okay, one more line like this. any field line that is entering, it is also leaving. Get the point. That means flux through a surface which is closed because of outer charges is zero. I'm repeating. We have taken here one surface which is closed, and we have taken a charge outside the surface, outside. Any field line that is entering, it is also leaving. Okay, that means electric flux through a closed surface due to outer charges is zero. So this is helping us while focusing on Gauss law. So when you are taking any number of charges outside, any number of charges, field lines enter and they leave. The number of field lines entering, number of field lines leaving, both will be same. That means net flux through that surface is zero. Okay, let's see notes for this. See what is given here. It is a measure of number of field lines through a given cross section. So more flux indicates more number of field lines. And how to calculate? That is using integral E bar dot ds bar. Okay. Direction of area vector is normal to the plane. Okay. And since it is now dot, it is a scalar quantity. Okay. And here note, area is a vector quantity. Its direction is normal to the plane. So this is about electric flux. Okay.